So this is a presentation of the paper Revisiting Traditional Curve Lofting to Improve the Hull Surface Design Process, recently presented at Compit 2012 in Liège. So an overview of the presentation starts to cover the question of why it is sometimes hard to produce a flaw-free surface. In the early stages, the surface can be quite quick to generate, but as we get to the stage where we want to incorporate some more complex features, we start to find that we cannot get that perfect surface that we're looking for. From this perspective, how can we say that curve lofting is relevant when today's surfaces dominate? And I'd like to show you how that is the case. And after covering how curve lofting can improve some of the surface design process, I'd like to introduce ways of combining both surface and curve lofting techniques, as surfaces are such a mature technology, we're really not going to replace them with curve lofting techniques. So we want to use the curve lofting approach to improve our surfaces beyond what we can achieve at the moment. So where are surfaces a problem? Let's start with a simple example, the simplest of examples. This is a very simple, almost idealized yacht shape, developed in a NURBS, and we can see the NURBS control polygon here. This is the kind of first thing that we would do when creating a surface. But very specifically with this kind of arrangement of control points, we find that very near the forefoot of the hull surface, with this particular arrangement of control points here, where we attempt to make the corner of the surface hidden, we introduce a concave effect in the waterlines. Now we'll not be able to remove this effect until we actually change the arrangement of these control points. So manipulating these control points can happen forever, but that shape will always be in there unless we resolve that particular effect. So where have we come from with our surface design, and where have we got to today, and why has it been a challenge to really develop good hull surfaces? So this is an example of my first hull surface developed many years ago in a NURBS surface. We can see that it's got all the characteristics of a hull surface, but now with experience, if I look a little bit more deeper, I'll start to see that I'd want to be able to manipulate the bulb shape in a little bit more detail, and this effect of this grid of points on the flat side doesn't give me the level of control of the buttocks very near to the flat side curve, and it also means that I've got quite a lot of points that are all located on a plane, not really necessary. So an extension of this type of design is maybe, well, how can we start to refine the surface if we want to add more points in one location and start to simplify it in another area? So an extension is to use more than one surface. Now this comes with its own challenges. Trying to join two surfaces together is quite difficult. It is mathematically possible, and with good care inside the software, a good match can always be retained. But for the user, this is very difficult to maintain this match. The constraints on them will be significant that they'd find it quite hard to really get the best out of the surface. So rather than manipulate the surfaces directly, using a grid of curves, say cross-sectional design, what we can do is give the surfaces to the software to generate, and what we'll do is we'll develop a mesh of curves from which the software can generate our surfaces. It achieves this through patch blending. So if we were to look at patch blending in a simpler idea of just blending a curve, if we had 2 points and 2 tangents, we can quite easily blend a curve through these, and it would be a cubic curve. To extrapolate that up to a surface, a similar idea. We have a surface with 4 edges. In the U direction, for example, we have 2 tangent or surface tangents along one pair of edges. And in the opposite direction, we have two sets of surface tangents. If we combine those together, we can generate a surface, a little bit more complicated than generating a curve, but fundamentally this is a surface that's entirely defined by its edges. That's quite a significant factor, because this means that the middle point of the surface is an average of all of the positions and tangent information on the edges. because it's an average, it's very good at filtering out any little indiscretions or discrepancies in the edges, such as small parameterizations that might not be particularly compatible or might not produce the best of surfaces. Because of this averaging process, it might mean that any mistakes are quite hard to identify. So how do we take this patch blending idea and apply that to a much larger surface assembly? So when we want to go ahead and generate multiple patch surfaces, we would start with a set of curves like so. Having provided these curves to the software, the next stage is that the software will first start to identify the vertices where the curves cross. It will identify edges attaching the vertices together, represented by curved segments. And once this topological assembly has been created, we can then start to identify the faces within this network of curves. Now, this process is fairly standard for many different CAD software, but it hasn't yet generated any surface information. So what we do next is process this assembly of curves and vertices and edges. So the first thing we need to do before we can generate a patch is generate the tangent information. And this is achieved by taking each curve in turn and assessing the curves that intersect with it and generate a tangent ribbon along those edges. That tangent ribbon is then subdivided by the edges that it exists within, so split down to the curves that cross it. And the tangent information for those individual edges can then be projected into the face area, and from there we can blend our surface as demonstrated previously. Now, this is quite straightforward for four-sided cases, but down on the bottom right we see that we've got a case where we have a five-sided face. For five-sided faces, we need to adopt particular strategies to solve this problem. That could mean that we start to use an n-sided surface, a surface that's capable of representing five sides, or we have to introduce a subdivision technique. And that's what's illustrated here, where we subdivide each edge in half, we identify a vertex in the center, and from there that subdivision creates a new set of four-sided faces, and we can have some four-sided surfaces. Okay, so the critical tasks in this process are that we have to interpolate the surface tangency, we have to address the cases when the number of sides of the faces is not 4, and then we generate our blend surfaces. Because we're no longer interacting directly with the surfaces, we do not necessarily need to worry about NURBS or surfaces with control points, so we have a selection. And the next issue that is quite challenging is to deal with the issue of compatibility between the surface tangents of adjacent edges, and this concept is often known as twist. So first, looking at our choice of patch, we have the ability to use any particular patch or surface that we might choose that fits the blending process. Pretty much we got a number of choices available. We could use our standard NURBS, we could go back and be very simple using something like a cubic Bezier, but there are also more unique surfaces available, say for example the Gregory Bezier patch, which overcomes some of the twist problems that we'll see later. The transfinite patch is a patch that's represented as a function rather than an assembly of control points like a NURBS. So it can be much more accommodating of things like twist, but when it comes to trying to get the surface on its own, it doesn't physically exist. It exists only as a calculation of information from our edges. And the final element there is much more modern introduction, is the subdivision surfaces. So we could use any of these for representing our whole surface. However, the main limitation in this respect is as far as working with other systems, CAD systems, and transferring the information around, only NURBS is supported by our industry standard file formats such as IGES and STEP. So, next stage, once we have our network of curves, we need to start interpolating our surface tangents. And again, this is another situation where estimation can get the better of us. So we take this central curve, and using the curve that crosses it, we can interpolate that, generate a representation of the tangent field along it, and this can be achieved by normal interpolation functions such as cubic splines. Now, one of the important characteristics of this arrangement is that curves that don't have anything to do with crossing that curve that we've highlighted there of interest have no influence on the shape of that tangent. And that means that possibly that tangent angle might not necessarily be the best for what we need. So this can be illustrated on this example here, where we generated the patches over that edge, and we see that that surface tangent has slightly misestimated the angle of the surface along the edge, and we get a small bump. Now, unless we interact directly with the surface tangent, the only way we have of really resolving that problem is to subdivide the surface along there, introducing one or two curves, as this example suggests. And you can see that the lines are now much more fair along that edge. However, we didn't really want to do this, and having done this, we now have almost doubled the number of patches along here. So refining the surface in this way to, so to speak, correct the software where it's misestimated it, can be a particular issue that ultimately generates us more surface than we really want. Okay, so now coming on to looking at issues of twist. This can be illustrated quite well of the limitations with control point surfaces such as NURBS. This is a simple example of a cubic Bezier patch, and the way that we would apply our tangents from the edges would be as illustrated here. So we could apply our U tangents, and that would get applied to these points. And then we would apply our V tangents, but we start to see the problem here that we've connected these to the same vertices. These two tangents are effectively locked because they need to connect to the same point. So even if we have estimated our surface tangency correctly, we might end up with a patch configuration where we can't actually apply that surface tangent to the surface. So what's going on can be illustrated in this particular example here. Say we take a four-sided surface, and on the top edge we bend that one upwards, and the bottom or the right edge will bend that one downwards. So if we now look at our surface tangents along the two straight edges, we see that for the left edge we're going to rotate that surface tangent in a anti-clockwise manner, and that starts to rotate upwards. And for the other bottom lower edge, we will rotate that one clockwise, and that surface tangent will start to bend downwards. Now in the left hand corner we see that the tangents are now going in completely different directions. We have quite a large discrepancy from our original plane for where that control point needs to be located. Because of this conflict, we have only one particular position where we can do it, which is pretty much to put it at the average position of those two vectors. This means that the surface doesn't constrain itself to the shape that we had originally wanted. Now this scenario is only working here for one surface in a corner. This happens at a vertex which could be part of our multiple patches. Now the limitation here is for a four-sided surface, for example, we need to connect up those corner vertices there so that they're all in alignment to ensure that we have complete tangent compatibility. This arrangement gives us a little bit of manipulation. We can think of this rectangular structure as a linkage where we can shift a point up and its opposing points will go down, but the linkage will follow through. For an odd number of patches around a vertex, to achieve that same linkage means that we've practically got to put all the points on a plane. And that means that again we don't have the ability to have the flexibility of the surface tangent as much as we previously wanted. Final item that we need to deal with is the case of the non-four-sided patch scenarios. This example here is very much an academic scenario where we have a nice blended or two cylindrical surfaces coming together. Often don't necessarily see that in a whole form, but we might need to use that kind of concept. A situation here where we have a rectangular patch that's been chopped off by the flat of side. And often we see these five-sided patches occurring very near features. So here, for example, we are near the bulb, and we have a five-sided surface. This is a particular interesting example because within reason we could do with quite a few more curves to explicitly define the shape of the surface here. But in this case it can be seen as quite an early design, so we're hoping pretty much that the software can come up with the best shape for us. So how do we address these scenarios? So for that particular scenario with the patch near the flap side, we could, for example, very simply connect one of the vertices to the other side of the patch, creating two four-sided patches. But sometimes if we have a more complicated shape, we might not be able to estimate that shape of that crossing curve too exactly. And in this case here we see that we've got a knuckle coming down from that top vertex. For more complicated scenarios, we might end up using the wrong subdivision method. So for subdividing that surface in the bow, we see we've got quite a ridge in the surface there where that edge is not necessarily the most appropriate one for that situation. This situation will probably be better solved with the regular subdivision technique. And we can see here that this surface tends to look a little bit more smoother, but even so there seems to be some strange things going on. There's a shininess up in the top left hand corner which looks a bit odd. And when we start to look at our lines here, we see we've got a significant ridge running across the patch where the tangency hasn't been estimated particularly well, and potentially that central vertex might be in the wrong position. Ultimately, what we would like to use in this situation is an end-sided surface that's entirely suited for the task, and that's what we see here on the right. That's produces a much better shading than the subdivided method that we see on the left. However, there aren't any end-sided surfaces that can be accurately written to our IGES or step file in the form of NURBS. So this is a bit of a challenge that we have these other surfaces that can represent these shapes, but we've got to take the limitation that we might not be able to export the exact representation into a file format so it can be used by other CAD systems. So this is the dilemma that the software developer faces when generating this multi-patch hull form representation tool. Because of these challenges, the users themselves will face quite a few frustrations. I mean, all of the surface design techniques are affected by at least some of these issues. There's no one technique where we can get 100% effectiveness. And because of the significant estimation that needs to go on in the surface itself, generating the surface tangents, dealing with the subdivision of faces and the blending process, we can often achieve many surfaces that are slightly warped, and because of the mechanism, because it's down to the mathematical mechanism, it can be quite challenging to resolve these effects. Because this is quite a large assembly, trying to find your way to limit the effect of these estimations is quite slow, and the software is quite complicated, so it needs some time to update. So it's not a rapid process, and we need a lot of patience. That said, we can find a fair surface. We use these techniques today, but it's something that has to be done with time and with patience. And finding that sweet spot can be quite elusive. There's no real tools to direct us towards that area that we're looking for. Often, surfaces are corrected by adding more definition. Definition and spending more time to basically force these issues out of the surface, basically fixing them. But often this means that we can lead us to quite complicated definitions where we have a lot of curves resulting in a lot of patches. It causes the software to slow down, making it more difficult to fare, and ultimately the performance is dropping in this particular case. So a little bit of a background. I occasionally get to use a tool called Lines, developed by Aviva. Now this is quite an interesting tool where the whole surface definition is entirely based on curves. It is capable of generating a surface, but the surface generation process doesn't really happen until you've got a fair hull form, and it's done in a very automated process. So the user does not fare the surface directly using the surfaces unless they're getting to the final phases of production. One of the challenges with Lines is that we see here a lot of curves, and it doesn't readily reveal the process or the workflow in how you actually generate the surface. And this is one of the challenges that I have to deal with in terms of training new users, trying to highlight or enlighten them about how they go about this process. The process is very manual. The user has the opportunity to control every individual point on every individual curve manually, but that would be a hell of a task to get this right. So there are some particular strategies that can be used to develop a fair set of curves. That said, all of the processes has to be invoked manually. It is possible to put all this into a macro, but it's not possible to run the macro at the call of the mouse, as in we move one point and get the macro to run directly, interactively. So in this respect, what I've attempted to do is take the idea behind lines and develop an automated process that can achieve that. So this was very much a kitchen tabletop bit of research, starting with a set of curves which we used in Polycad to develop the X-topology surfaces. So these are X-topology curves. And we simply intersect these curves using a set of planes, and for example here to generate a set of waterlines. So this is kind of simple cubic B-spline curves using algorithms out of the NURBS book, for example, and we just throw a set of planes through these curves, get a set of intersection points and fit a curve through them. And then we repeat that process. So we repeat that process for a set of buttocks, for example, and for a set of waterlines. And because we're only dealing with cubic splines, this process is incredibly quick. But it does start to pick up some interesting facts about our curves. We can generate the curvature straight away from our curves, far easier than trying to evaluate the surface. And we can see, for example, here that the surface, or the implied surface that we're creating, might not be as fair in particular areas. So perhaps the curve compatibility isn't that particularly good, even though it kind of looks fair. We could also, in this case, change the process. So, for example, say we fitted the waterlines, sections, and then buttocks, and we have a much fairer representation of what's going on. But we start to see some of the limitations of an automated method, that it doesn't necessarily pick up all the information that we want. So, for example, on the final stage of applying the buttocks, we've missed some of the curves that we've done earlier. So, this automating this process is very good at highlighting where curves are compatible, being very quick, but it's not a perfect solution for surfaces. We might end up with particular areas where we need to add more definition to make sure that we're explicitly defining how the surface should be. So some of the quick experience of using this technique was that it's incredibly fast compared with a surface technique. In many cases 2 orders of magnitude quicker in terms of, say, the curve lofting method working in the order of milliseconds, whereas the surface method for the same set of curves would probably take seconds. It's extremely simple to code. I think in terms of development, I spent about 3 weeks on developing this method, whereas X-topology surfaces were developed over a period of 3 to 4 years. Because it's so simple, it's incredibly robust. We no longer have to worry about the topology of the curves, where the curves are connected. We can practically give it rubbish. And because the curves, the splines that are being intersected through these definition curves are only based on point proximity, it's very difficult to come up with a scenario that could cause the software to crash. And because of that, it's a very tolerant process. We can use this to kind of identify a hull form before we get to the stage of worrying too much about our surfaces. If we were to look at the process in more detail, we see that this, compared to the surface approach, is global interpolation, which is quite interesting. It means that curvature is being maintained as being smooth across all of our curves if we allow it to. This is unlike the surfaces in our previous example, where the blending only takes place between local curves, and fundamentally it's local. So we're relying on the software to match the curvature between those surfaces, but cubic blending doesn't match curvature, it only matches tangency. So there's quite a discrepancy between the kind of smoothness that we'd like to get from our surfaces, which we're limited to because of the local interpolation. But the curve method can smooth that curvature around because it uses global interpolation. because we're now lofting from different directions, and unlike the blending approach which tries to average everything together, if there are mismatches between curves, these are highlighted quite well. Either the curve will vary in its location across the screen quite violently, or if it's not visible, we'll start to see discrepancies in the curvature. And as highlighted in that previous example, automating it does somehow start to limit the performance of it. It's not like a surface where it will fill everything in. If there's a gap in somehow an edge, or there's not enough information in a particular area of the surface, this technique is not very good at estimating the shape of it. That really comes in when the blending method is used. And because this is so quick, such a fast and simple method, it has, I believe, a potential to change the design process when we're trying to generate surfaces. And we'll start to look at that in the next slides. So it's quite good at identifying subtle mistakes. This is a fairly simple yacht surface, for example. We can't see any mistakes on the face of things, but if we were to look at curvature around the midship section, we see that we've got quite a perturbation of curvature around that midship section definition curve. And this is down to the fact that the midship section curve has a slightly different definition to the section curves that are neighbouring it. And because it's slightly different, there's a change in curvature. So what we need to do is change that midship section area curve so that it has the same definition of our sections. In this case, it's quite an easy one to resolve, that we can just remove that curve from the definition so that it affects some of the other definition curves, but it doesn't directly contribute to the loft. And now we get a much smoother shape in our surface. So, having generated this implied surface represented by loft curves, this definition uses exactly the same as the surface, the X topology surface. So an opportune thing to do is compare the surface generated by our lofted curves with that generated by our surface. And this is the sort of thing we start to get. Surprisingly, for the most part, we see that a lot of the curves coincide. So here we have a hull form just showing the buttocks. These buttocks at one level are coming from our surfaces that have been generated across this curve network, and there's another set of buttocks that are being lofted by curves using exactly the same method as previously described. So we start to see some discrepancies. We start to see some discrepancies in area of the surface that aren't working too well. For example, we start to see some discrepancies down the flat of side here. Now these aren't the most obvious discrepancies that are coming out. They're definitely around the bulb, but we can see a buttock coming out on the surface here, illustrating that we haven't developed these curves so they have the best tangent into the flat of side curve. We can see in more detail here with these yellow curves. The yellow curves are coming from the curve lofting, and the bluish curves are coming from our surfaces. And we can see that our surfaces are bouncing around, whereas our lofted curves are quite smooth. And both these outputs are generated from the same loft curves. So what we have here, or generated from the same definition curves, so what we have here is a case where these definition curves are causing some problems in the surface generation process, and we can see that in the fact that they are different from the curves that are generated from the lofting process. So having this discrepancy highlighted, we can now go into the definition and use the lofting method to smooth this out and achieve a better surface by going through that process. So around the bow we see quite a significant amount of discrepancy, and this really is down to the fact that there's not enough definition in this area of the surface. Really what this means is now we have to put some more curves in here. We have to be more explicit about the shape that we would like the system to generate for us. So I need a little example to show this process. So this is that original surface that we saw there earlier. It would take some time for me to go through and improve that surface in front of you. So we'll highlight the improvement that we can achieve with some isophotos. So these are the light falling on the surface and the different colours of curves of the angle the light makes with the surface. So we see around the flat of side area around here, we can see quite a big discrepancy in the tangency between these two curves, basically meaning that we haven't got a very good smoothness in the surface. And that's also a case around the bow, around the bulb. I'm going to purely focus in this case on the flat of side to give a better illustration. So after about half an hour's work, this is the level of improvement that I was able to achieve. We've now got a much smoother surface around this flatter side. It's not yet perfect, but it's much better than it was. Of course, we can carry on and get the smoothness of surface by spending more time on it. But the nice thing about putting these lofted curves on top of the definition that generates our surface is that they highlight where our surface was unfair. So that's compiling the surface and the curves visually, doing a qualitative assessment. Why not, given that these curves have global interpolation characteristics, use them to generate the surfaces that we're actually looking at? And we can achieve that quite easily in that respect. This is something that Aviva Lines does quite readily to generate its surfaces at the end. So we see a set of loft curves here, and we can generate some information ready for a least squares fit, for example, by sampling these curves and getting some data points. And then using these data points, we can then fit a surface to these curves by doing a normal least squares fit. We could use our original surface to kind of give us an idea of the parameterization, and at this level, this is a fairly straightforward approach to take. So this is the sum of the effects we can see. The top one is a surface generated by blending our patches between these definition curves, and the bottom case is if we take the curve lofted curves and sample them and generate a surface using our least squares fit. And even though both of these surfaces have the exact same definition, the bottom curve here bottom surface here illustrated with Gaussian curvature is a lot smoother in the way the patches are generated. That said, we have a few problems around particularly small patches in the second case at the bottom. This is occurring because we have a certain density of loft curves, and as we get down to the smaller patches, we see that the amount of sample data is starting to greatly reduce and not giving us the ability to create the best type of patch. This can get worse. We can see in this particular case where the surface data around the bulb is clearly not enough. We get quite a lot of unfair surfaces, and with the particular solver that this case is using, we've got quite a lot of peaks and troughs looking like a very poor surface. But in other areas of the surface, we can see that it's performing quite well. So this is still a work in progress, still trying to identify the best ways of regenerating our surface in this area. One of the benefits of going through this process is that we can't see very well there, but a lot of the subdivision curves can be re-estimated, refitted to the lofting curves, and that means that we can improve our original estimate of this shape. So finally, how can we use this to improve the design process? Well, this will be very much an illustration of the existing definition process. We start with our definition, we move some points around, we assemble them inside the software, then the software goes away and generates the surface. Then, using the graphics or the curvature analysis, we can see how well we are doing with our points. And the limitation then comes that it's then up to our own experience, our skill, in how we would go forward and change the definition. Where curve lofting can help is that it gives us in many ways a second opinion on the definition curves we're putting in. It's quite capable of showing you if our definition curves are fair or if there's some sort of mismatch. And working between the surface blending and the loft curves, we can start to improve our surface to try and get it better, with our way directed by the discrepancy between surfaces and the curve lofts. Then we could combine our two in a surface fitting process and achieve a much better surface because the curves lofts have the benefits of the global interpolation. In both cases we can use our standard analysis process. So this isn't strictly an alternative way of generating a whole surface. We still have the same characteristics of other methods where we start with the definition when we do the surface blending and then we do our analysis, for example. This gives us a way of adding or having an extra tool which we can use to identify where we need to direct our attention in correcting the definition. So concluding our presentation now, the whole surface design process can get frustrating. This is often down to the need to incorporate different features into our surface, and when we do that, often small mismatches can cause warping of our blend surfaces, or little things that we might introduce that causes our surface to just behave in a way that we don't expect. Because of that, it can be really difficult to identify these poor shapes. We can't really have a system where X marks the spot and there is some system that tells us how to correct it. Fairing tools allowed us to smooth the surface, but if, for example, there's a mistake in the parameterization, or there is some connection or some topological reason why the surface cannot be produced in exactly a smooth way, fairing is not going to give us the ability to move or improve the surface. We can move the points around all day, but we might continue to have a problem. So, interestingly, curve lofting is a fast and simple approach, particularly when it's made interactive, really robust. And because it's not necessarily doing the same as our blend surfaces, it's trying to generate shape from a number of different directions which are often not completely connected. It's very sensitive to these poor connections between different curves, and these poor configurations often highlight there's more of a cause in the definition curves, which are the same reasons why we would get the same problem with the surfaces, that these poor configurations just create poor shape. And in the particular case in PolyCAD, we have the opportunity to use the same definition curves as the surface is using, so we get the opportunity to overlay the two effects. And that concludes the presentation.